Hi students. In this lecture, I am going to discuss time varying magnetic field. Let us see. Consider a loop which is a conductor. I am taking a loop here. It is a conductor and I am taking this board plane as XY plane. Assume that a field is present, magnetic field is present, normal to this plane. And assume that this field is now constant. That means flux through this loop is a constant. Okay. And here initially there is no flow of current in the loop. That means electrons are stationary. They are at rest. So at rest in the sense, we are not taking a random motion. Okay? We have learned that electrons will move randomly in all directions, even though there is no battery present or no current is flowing. But here we are not taking the random motion. That means electrons are now at rest. And on stationary charges, magnetic field exert no force, right? So here there is no current. Now, assume that magnetic field is changed. That means flux through this loop is changed. And because of that, a current flow is observed in the loop. So now question comes. Initially electrons were at rest. Now they are moving. So what is the cause for the motion of electrons? So we have learned that on stationary charges, because of magnetic field, no force acts. That means this force is not magnetic force. Then the only possibility is now electric force. So from this we conclude that because of a time varying magnetic field, an electric field is induced or an electric field is produced. This is the conclusion of this. And remember, for this induced electric field, presence of this loop is not required. It is not mandatory. That means assume that there is no conducting loop. This is now vacuum. In vacuum, magnetic field is present, which is now changing with the time. That means its modulus values change. Still, it is going to induce electric field. That means even though loop is not present, electric field is induced. Okay, right. And if you remember earlier, we have learned in electrostatics, electric field is present because of electric charges. And that electric field is conservative, right? And there we have learned field lines start from positive charge and end on negative charge. That means those field lines are curved. They are open curves, okay, like this. And here we define potential because this field is conservative. But coming to here there are no charges are present. This field is due to because of a time varying magnetic field. So this is now entirely different from this electric field, which is due to charges. So electric field due to charges is a conservative, but electric field due to time varying magnetic field is non-conservative. Since it is non-conservative, here we do not define potential. Okay. And next, one more important point is here field lines start from positive charge and end on negative charge. But coming to here, there is no starting point and no end point. That means in this case, field lines are closed. Okay. These are now major differences between the electric field due to point charges and electric field due to time varying magnetic field. Okay. And see, in Faraday's law, we have learned EMF induced is equal to negative of rate of change of magnetic flux with respect to time, right? and this EMF is written as closed integral E bar dot dl bar. Let us see once what is this. If you remember, while discussing current electricity, there we have defined for a battery what is an EMF, right? I am recollecting once. Let us take this is a resistor which is connected to one battery whose EMF is now E. Okay. And we are knowing that a positive charge moves off its own from high potential to low potential. You can see here. Suppose I am taking here a positive charge in the wire. This positive charge moves off its own from high potential to low potential. You can see this is now high potential and this is now low potential. So positive charge moves off its own from high potential to low potential of its own. But from low potential to high potential, they cannot move off their own. So here battery is doing work to pump these charges from low potential to high potential. Then only we can expect a continuous flow of electrons, means continuous flow of current. So electric current is now like this. That means electrons are flowing now in this way, opposite, right? So here EMF is defined as the work done by battery in a closed path. So when you are taking work done, we have to take actually F bar dot DL bar, right? DL bar is displacement, F bar is that electric force because of the battery. And here we are taking now EMF is defined as work done by the battery per unit charge or per unit positive charge. That means in the place of F bar, it is now 1 into E bar. Electric force equal to Q into E bar. Here we are taking, it is defined as the work done in moving a unit positive charge in one closed path in one round, right? That's why taking the place of Q, it is a plus dot DL bar. Okay. This is what I have written here. Closed integral E bar dot DL bar, right? This is here E bar is now induced electric field, which is non-conservative, right? Let us focus now. The points till now what we have discussed. Right, you can see here. First point, electric field due to charges is conservative. Electric field due to time varying magnetic field is non-conservative. Electric field lines are open curves. They start from positive charge and end on negative charge. Electric field lines are closed curves. Here there is no starting point and no end point. Coming to here, potential is defined, but coming to here, potential is not defined. Okay. Let us focus now problems to get more clarity. See the first one. A uniform magnetic field exists in a cylindrical region of radius r. Find the strength of the induced electric field at a distance r from the axis of the cylinder if the strength of the magnetic field is changing with the time. Right? Let us see. Right, first make a diagram. Condition given that magnetic field is confined to one cylindrical region. Confined to one cylindrical region. If you take now this both plane as xy plane, length of the cylinder is now along z axis. That means the field is now along z axis, or you can say along positive z or negative z. So I'm taking now field is along negative z, means into the board. Now strength of this field is changed. Okay. So we want to calculate now strength of the induced electric field as a function of distance from center. So now what I am saying is consider a circle by taking the distance as radius. So consider one circle by taking that distance as radius. So by symmetry, we can guess that strength of the electric field at each and every point on this circle, it will be same. Okay, that is what we can say. Now we want to use this one closed integral E bar dot dl bar, that is equal to minus d phi by dt. So using this Faraday's law now in this case to find strength of E bar, right? And before that, first we should know what is direction of E bar. Okay. So when I'm taking here a loop, so when I'm taking a loop here, the first condition is that if you remember while discussing Gauss law, electric flux is equal to net charge inside the surface which is closed upon epsilon naught, right? But coming to here, in this region, no charges are present. That means through this loop, no field line enters or no field line is leaving. That means at each and every point on the circle, direction of the electric field must be tangential. It must be tangential. In that case, no field lines are coming outside or no field lines are entering. This is what we can say from Gauss. Therefore, at each and every point on this loop, or we can say on the circle, direction of E bar is along the tangent. Okay, right. Now see what I am doing here. If I am taking here a small length on this loop, we are taking out direction of DL bar as direction of E bar. Then see what I can write here. Closed integral E into DL into cos of the angle. That is now 0. And see carefully here, direction of the electric field. The question comes like, when I'm saying tangent, is a tangent like this or like this? Okay, let us confirm that. How to decide? Suppose this is field is now increasing. That means flux through this loop is increasing. And according to Lenz's law, direction of the induced current is in such a way that magnetic field due to induced current is opposite to the existing field because this is now increasing. Okay, so this is now into the board. Therefore, due to induced current, magnetic field must be outwards. That means towards us. So keep the thumb of right hand towards us, curl fingers. Now curling fingers, they are anti-clockwise. That means electric current is now anti-clockwise. That means if I am focusing a positive charge on that positive charge, because of electric field, force will be in this way. At this point, force will be like this. At this point, force will be like this. That means, first of all, we can decide direction of current. That is now anti-clockwise. If I am taking strength of the field is increasing, that means in this case, this is now tangent along the field direction, right? So E into dl into cos 0, that is equal to, so here dl means we have to focus that loop. Okay, this is the loop we have chosen. Then see what we are going to get, minus, coming to here area is not changing. This is a pi r square into dB by dt, right? Let us focus here only modulus value. No need to take here negative sign. Just focus modulus value because direction part already we got here, right? Which we are deciding basing on is a flux increasing or flux is decreasing. So I'm focusing only modulus value. So E into closed integral dl, that gives us 2 pi r. That gives 2 pi r. That is equal to, I am focusing only modulus value. That's why not taking minus pi r square into dB by dt. Okay. Right. Now see what we are going to get. Pi gets cancelled. One r gets cancelled. Remaining is now E equal to r by 2 into dB by dt. This is when r is less than or equal to cap, right? This is inside the cylindrical region, means inside the magnetic field region, right? Suppose if this r is now greater than capital R, that means we want to find out outside. Then see what we are doing. Then we are taking now loop is like this. So we want to calculate now outside that cylindrical region. So then we are taking the loop like this. So again, it is E into 2 pi r, that is equal to, coming to right hand side, this value. We can see flux is confined to only the cylindrical region. If I am focusing flux through this entire region, that is equal to again flux through this cylindrical region. Okay. So here we have to write pi r square into dB by dt. Okay. Pi gets cancelled. E equal to r square by 2r into dB by dt. This is for r greater than or equal to capital, right? So like this we can use, okay, Faraday's law to find the strength of the electric field is induced. Okay. And if you want to plot a graph for strength of the induced electric field as a function of distance from the axis of that cylindrical region, then see how the graph is. So you can see up to surface, it is changing linearly. Changing linearly up to surface. That is r equal to capital R. After that, you can see here r square is a constant, dB by dt. It may be constant, but because we are focusing only with the distance, okay? So E proportional to 1 by R, right? Only focusing with the distance. This is now E proportional to 1 by R. So E proportional to 1 by R. This is now graph for modulus of induced electric field versus distance from the axis of the cylindrical region. Okay. Let us take one more problem. Let's see the question giving. A uniform magnetic field exists in a cylindrical region of radius r. Consider a non-conducting ring of mass m and radius r having charge q. Its center is on the axis of the cylinder and its plane is normal to the axis of the cylinder. Find the angular velocity of the ring as a function of time if the strength of the magnetic field is changing with the time, and given initially the ring was at rest. Okay, let us see how to start. Right, first of all, see the given data. Magnetic field is present in a cylindrical region. In a cylindrical region, and given that radius as Kepler. Consider non-conducting ring of mass m and charge q, and given that its radius is now smaller, which is less than Kepler, and a condition given that its center is now on the axis of the cylinder, right? And plane of the ring is normal to axis of cylinder. It is like this, right? Initially, the ring was at rest. Its center is on the, okay, right, it is over. Now we have to calculate angular velocity of the ring. So we have to calculate angular velocity of the ring if magnetic field is changing with respect to time. So dB by dt, this is a non-zero value, right? Let us now take this as some constant. It is k, constant k. Right. Now see how to start. So first we are focusing. Since he is asking omega value, initially omega value is 0. Now we have to find omega. That means there must be a torque acting on the slope because of which a ring rotates. So first we are focusing how torque is produced. Okay. So I'm taking here loop separately. So taking loop separately. And just now we have learned, right? What is strength of electric field? Strength of electric field inside, that is equal to, it is R by 2 upon dB by dt. That is taken as a k, right? Now I am taking a small charge on the wire. Taking a small charge on that wire, it is now dq. Suppose field is now increasing. I am assuming that field is now into the board. When field is increasing and it is now into the board, through this loop, flux is increasing. Because of increasing flux, electric current is now flowing in the wire. Now direction of induced current is in such a that magnetic field due to the induced current opposes the flux. So here field is now into the board. Due to induced current, field must be outwards, that is towards us. So keep thumb of right hand towards us and curl fingers. So current is now anti-clockwise. That means positive charge moves now anti-clockwise. That means on this, electric force will be like this along the tangent in this way. That is now dq into E, right? And torque due to this force, if you calculate that, that force into R, right? That is torque. Like this on each and every element, same force means same modulus of the force acting and same distance. That means net torque is equal to, see here what I'm writing is integral dq into E, that is a force, into R, that is a torque. Now we are calculating net torque. E is a constant, R is a constant, integration of dq, that gives total charge. So Q into E into R. This is net torque. So this net torque equal to This net torque is equal to Q. In the place of E, I am writing R by 2 into K, right? Into R. This net torque equal to I into alpha. Since it is a ring, since it is a ring, I value about its own axis, mr square, I into alpha. Now see calculation. R square gets cancelled. R square gets cancelled. Alpha equal to, it is a kq upon 2m. We can see alpha is a constant. Since alpha constant, we can write omega, that is equal to initial value 0 plus alpha. So omega equal to, or omega 2 equal to omega 1 plus alpha. So alpha is known kq by 2m into t, right? Like this, we can calculate angular velocity of the ring, right? Let us take one more problem. Right, see the question given. A uniform magnetic field exists in a cylindrical region of radius r. Consider a non-conducting ring of mass m, radius r, having a charge q. Its center is on the axis of the cylinder and its plane is normal to axis of the cylinder. So almost same as the previous problem, right? See here where change comes. Find the angular velocity of the ring if the strength of the magnetic field is changed from 0 to B suddenly. Initially ring was at rest. That means in the previous problem, magnetic field was changing continuously. But coming to here, it is changing suddenly from 0 to B. That means torque is acting on the ring only for fraction of seconds, for a small time interval. See here what I am writing. We will take the results of the previous problem. First of all, torque. First I am writing here E value, E equal to R by 2 into dB by dt. E value, right? This is what we got. Next, coming to torque. Torque, how much we got? See in the previous question, we got torque equal to charge into this field. See how much we got at field. Charge into R by 2. That is R by 2 into dB by dt. The C is a force. Actually, we have taken dq, right? dq into this value force into R. That is now torque acting, right? Then we have taken integration. Then we got this value. This is torque, right? Now condition is given that B value changing. It is from 0 to B in a small time interval given suddenly, right? Then see what I'm doing here. I'm taking here net impulse tau bar into dt, that is equal to change in angular momentum. Okay. So this is now how much? Since it is a constant, I'm taking this outside. The remaining is now integration of dt and that becomes t. Wait, this is not a constant, right? Let me substitute this value in this one. Q r square by 2 take outside. Q r square by 2. Q r square by 2 outside. Integration of dB by dt into dt. That is equal to I omega minus 0. Okay. Right. Now see the calculation. Q r square by 2 Now here I can cancel dt and dt. This becomes now directly b minus 0. It is b. That is equal to further about its own axis. I value mr square into omega. R square gets cancelled. So here omega is equal to qb by 2m. qb by 2m. So this omega is a constant. In the previous case, we have seen that field was changing continuously. That's why in that case, omega, it was depending on time, right? But coming to here, omega is a constant, right? So I hope you got a clarity.